Thanks everyone for joining, and big thanks to Dr. Paul Wighton for taking the time and giving this very interesting and very useful tutorial slash review talk on perspective motion correction detection techniques. And so, just to give a brief biography, Paul received his bachelor's. Well, I call him Paul because we were, I guess, buddies and graduate
You can
students
call me
together
Paul.
back in this.
That's fine. That's what I
Yeah,
prefer anyway. So.
yeah. So we were graduate students and together in Vancouver at Simon Fraser University. So yeah, he's received his bachelor's in engineering systems and computing from the University of Guelph in Ontario, and PhD in computer science from Simon Fraser University in BC. He later did his postdoc at the Martinos Center of Biomedical Imaging at the Mass General Hospital in Massachusetts, where he worked on real-time MR applications, specifically real-time fMRI neurofeedback and prospective motion correction. He then went on to do some very interesting work for a startup and then helped secure a FDA 510K clearance for a software package based off of FreeSurfer. And then he's now back at the Martinos as a senior R&D engineer. So thank you very much again, Paul. So without further ado, please go ahead.
Thanks, Pradeep. Hi, everyone. Nice to be here. Just one quick note, as you know, Murphy's Law would have it, about 15 to 20 minutes ago, a construction crew just pulled up outside my window. So I really hope it doesn't get too noisy, but I'll just persevere. Okay, can everybody see my screen here? Oops. Is that, can people see that? The title slide there?
Yes.
Okay, great. Okay. Yeah, so, you know, we can keep this discussion informal. Feel free to ask any questions as I'm going. It's just one note, I can't monitor the Zoom chat while going through the slides. So if there is comments in the chat, maybe Pradeep, you can just read them out because I won't see them, or I can take them at the end. Either way's fine.
Yeah, I mean, feel free to speak up. You all can speak up anytime, you know, you have the permission.
Great, okay. Yeah, so today I'm gonna talk about, give an overview of prospective motion correction techniques in MR neuroimaging. And just a bit of motivation for why we're working on this problem. There was a great paper. One other just quick logistical point. Can people see my mouse if I move it around on the screen?
Yes.
Okay, great. Okay, so I can point at stuff. That's perfect. Okay. So as a way of motivating, Dr. Andre Jalal has a great paper on the costs associated with motion in MR. And he concluded that on average, it costs $115,000 per scanner per year in either lengthening acquisition times or having to bring patients back to get rescanned. You know, and if you just look up the density of MRIs machines in America, you know, some simple arithmetic will lead you to the conclusion that motion during MR acquisition is a $1.5 billion a year problem. So there's a lot of motivation to solve it. And, you know, so here's a slide up front of what we're trying to accomplish. Essentially what we want to do is take acquisitions that without any sort of motion correction might look like the top row here. And we want to make them a lot more crisper, clearer, like the bottom row here, make them diagnostic quality. So there's a bunch of motion correction techniques, MoCo as we call it, but they can broadly be categorized as either prospective or retrospective. So retrospective techniques is anything that you do offline with the data after you've acquired it. Maybe you save all of the case-space data. Maybe you regrid your case-space. Maybe you regrid case-space for motion, or maybe you're using like some sort of e-spirit operator to, interpolate places where case-space wasn't acquired. And those all work really well, but I focus mostly on, and what I'm going to talk about today are the prospective techniques. That is, there is some mechanism to track how the subject is moving in the scanner, and that information is fed back to the scanner controller, and the pulse sequence is modified on the fly to realign the field of view for the patient's, to keep it aligned with the patient's head. And the biggest motivation for this is, if you don't acquire a certain part of case space, there's a lot of maybe tricks or techniques you can use to infer what would have been there or deal with that, but nothing will beat actually getting the case space data as it was. And that's the main motivation for this. Prospective also gives you the option to do something which is called reacquisition. So if we know the patient moved during TR 17, let's say, we can add that to some sort of queue, so that at the end of the scan, we'll go back and reacquire that particular TR where case space was damaged. So now focusing on prospective motion correction itself, the techniques can be largely divided into two more categories. Those are navigator-based techniques. That is using only the MRI system itself to infer head motion, so no extra hardware. And then there's a whole bunch of external trackers that involve augmenting your scanner with other hardware. Maybe it's a camera, maybe it's some field probes, or something that will help you track the subject. All right, so let's start with, and just as in a way of disclaimer, a lot of what I talk about might be Siemens scanner specific. I'm going to try and use the generic terms, but all my experience is on Siemens scanners, so I can't help but fall into that language sometimes. So I apologize for that. But let's just start with one of the earliest and one of the simplest prescriptive motion techniques, and that's with your bold sequence. If you're doing an fMRI acquisition, you're acquiring the same volume over and over again. Every maybe 2 or 3 seconds traditionally, or now with like these multiband sequences, less than a second. But the idea is like all you're doing is acquiring the same image over and over again. So what PACE did very early on is all it does is it takes one of the volumes from your bold series, it transfers it to a registration algorithm. That volume gets registered to the very first volume that was acquired. The motion estimates are computed. Everything we deal with here is rigid motion. So we're computing 6 parameters. 3 parameters for translation and 3 parameters for rotation. That's almost always the problem being solved in prospective motion correction. So that does a simple registration of 2 bold volumes, infers these parameters, sends it back to the scanner, the field of view is updated, and away you go. PACE is actually interesting because it's both prospective and retrospective. So you could not feed the updates back to the scanner itself. That's an option on the scanner, and simply just register the series when you're done. Or you could only do prospective, only feed the position updates back to the scanner. Or you could do both, right? You could update your position, and then when you're done the scan, you do an additional registration of all the volume to account for any residual motion that might have been there. So that's the very basics. Every other technique I talk about kind of builds off that fundamental concept that you're estimating 6 degrees of freedom. You're sending those estimates.
Can I ask a question?
Sure. Yep.
Is this actually useful in practice? Because say if you could adjust the scanner in real time, right, according to what's provided by PACE, and presumably you're only correcting volume to volume motion, aren't you? Which you could do offline. Do you see what I mean?
Yes. It's a good point. The utility. So I guess prospective PACE would be the most useful if the motion was so great that the person moved outside of the field of view.
Yeah.
But to be fair, if that happened in EPI, you run into a whole host of other.
Yeah, I guess you have a whole range of problems then.
Yeah, absolutely. And motion in EPI sequences is more brutal than anything else. So it's a good point. I mean, we always used when we were doing it, we used prospective PACE, but I know a lot of groups that don't. I know a lot of groups that would only
slice-wise maybe.
I will not with PACE itself. Later on, I've worked on that with some external trackers. If you have that information, right, you can do it. Yeah. You can do it slice-wise, and I'll get to that. But the benefit is minimal, at least what I was able to achieve. Again, because bold is or EPI readouts are so brutal, and there's so many like B0 effects. So many other effects you need to consider.
Okay, thanks.
Mm-hmm. Yeah, go ahead.
No, just say thank you.
Oh, I thought Pradeep. Pradeep, did you said you had a question?
No, I saw it was on actually a previous slide. It was interesting. You called not you. I mean, why the first section is called Navigators, although they don't actually navigate in a way, you know, literally speaking.
Yeah, that's the word that that's what it's always been called. I guess it helps you. Yeah,
navigate
why is it called
K-space? Probably, you know. Yeah.
Well, it's not even navigating K-space. It's I guess it's inferring how the subject navigated, or yeah, navigators. Yeah.
Right.
I don't know.
I guess the locus is the subject.
Yes.
Yes. Yeah. Oh, yeah. I was just curious if there is another reason why they are called like that. You know.
It's honestly a good question. It's something I've never thought of, but it's what everyone calls them. Okay, so that's PACE, and yeah, its utility prospectively can be questioned or could be minimal, but it's useful to illustrate the core concepts here. We've got some method of inferring motion, and then we're feeding that back into my apologies, into our scanner in real time.
So maybe you touched on this quick question, Paul. You stressed the motion estimation is rigid 6-parameter, right?
Yes.
Is it broadly understood that's all we need? Maybe you'll talk about it later, but you know.
I don't. I'm hesitant to say that's all we need. It goes a long way in neuroimaging. I don't have much experience at higher field strengths above 3T. It's certainly possible that things like blood pressure and pulsatility have some sort of effects at higher field strength. that's not something I know much about. So what I can say is that for 3T and under, it goes a long way to improving your scans. If you're doing something very cutting edge at 7T, you might have to make use of additional techniques, but I can't say for sure. Okay, so that's pace. And then just to build off that a bit, so the obvious extension to pace is like, would it work on diffusion, right? It's another EPI-based sequence where you get a bunch of images every few seconds. And the challenge in diffusion is, you can't simply, okay, so in this image here we see a B0. So this is just like an EPI image. And then here are, 6 diffusion directions. It's challenging to register these directional images to each other. So applying pace directly in diffusion doesn't work so well. But there's some techniques that people have come up with. One is if you're doing multi-shell diffusion, you can register the direction to that of a previous direction and infer motion that way. But what I think is really interesting is this second paper here. What they do is they reorder the diffusion directions of their sequence such that any 3 directions and any 3 consecutive directions are approximately orthogonal. And if that's the case, so if they were perfectly orthogonal, then you could compute a trace image and then register that. So what they call these images pseudo trace images. They're not perfect trace images because they're not perfectly orthogonal directions, but these authors argue that it's close enough to get these pseudo trace images, and once you have those, you can register them much like you would do in bold, and keep going. So here's a figure from their paper. They start by reordering the diffusion gradient vectors into overlapping subsets of 3 consecutive vectors where there's high, they call it mutual orthogonality. They acquire a volume. They use the volume that was acquired plus the previous 2 volumes that were acquired to compute a trace image. And then much in the same way that the bold is registered to the initial reference image, this trace image is registered to the initial trace image, and the motion estimates are updated accordingly. One other thing to point out in diffusion, not only do you need to reorient the field of view, you should also be reorienting your diffusion direction when you change the field of view. Okay, so another broad technique are these navigators. There's navigators that work in K-space and navigators that work in image space. There's a bunch of different types of K-space navigators. Here I've listed some of the more common ones. They're mostly described by the trajectory they take through K-space. So there's orbital navigators, spherical navigators. What this image here is of a cloverleaf navigator, which has some complicated trajectory where it goes through the center of the sphere and then around one of the edges and then through the center of the sphere again. It ends up going through the center 3 times and then around the edges 3 times as well. And then there's also something called an FID navigator, a free induction decay navigator, which is essentially all you're doing is looking at your coil loading on a multi-channel coil. That one's a little special. I left it off this list here because that one doesn't let you correct motion. It will only tell you that motion occurred. It can kind of give you some indication of the severity of the motion that occurred, but it won't tell you these are the translations and these are the rotations. Whereas these 3 techniques here will do that. More recently, people have started moving away from case-based navigators to image-based navigators. I would say the advantage of case-based navigators is they're shorter. For example, here, this is from the VNav paper. These are image-based navigators. So essentially, what you're doing is you're taking your sequence, whether it be an MP range or a T2 space, and you're essentially inserting a tiny little bold sequence into that, so that you can do the exact same thing that PACE does. You collect a low resolution image, you register it to the first one, and then you play your parent sequence, play another navigator, and do the same thing. These navigators are much longer than case-based navigators. For example, VNavs here, and it's VNavs for Siemens, and it's Promo on GE. These are 355 milliseconds. And for some sequences, that works really nicely. So for example, these two sequences here, multi-echo MP range and T2 space, there's natural gaps in the sequence anyway. In the case of the MP range, there's the TI gap. And in the case of the T2 space, there's a TR gap where you're waiting for relaxation. So you get the navigator for free, essentially, because there's this dead time in the sequence where you're waiting for something to happen anyway. That's not always the case. Sometimes they'll increase the length of the acquisition, but sometimes with some clever planning, you can get it for free by inserting it into the dead times of the sequence. So the big benefit of image-based navigators is you can operate on an ROI. You can perform your registration on the regions of interest you care about, and that's hard to do or to do with case-based navigators, or kind of looking at the bulk motion over the entire field. But for example, in image-based navigators, so this is an example of the low-res navigator you get out of VNavs. And it shows the whole head, and you can see like the jaw and some soft tissue here. In practice, this isn't a navigator we would use, right? In practice, we would choose the field of view for the navigator so that it only contains the rigid part of the brain we care about. We want to discount the nose, we want to discount the jaw and the neck. And we can place the field of view only on the rigid part of the head and skull, because that's what we care about tracking. So a quick review. Navigators are great because they require no additional hardware. So it's purely software. It can be deployed at scale. It's just as easy to send the sequence to one site it is to 100 sites. They can operate either in case-based or image space. Case-based navigators are generally faster, but image-based navigators allow you to really drill into the anatomy that you care about and make sure that's the motion you're tracking. And they're constrained. They're both constrained by the underlying sequence. Image-based navigators more so than the case-based ones, but either there's dead time in your sequence where you can insert one of these, or the total time of your acquisition has to be extended. Okay, so moving on from navigator-based methods to tracker-based methods. So now we're not going to use, well, we might use some properties of the MR system to track motion, but what we're doing here is we're throwing additional hardware at the problem to help us track. And these largely break into two categories. There's what's called field probes. So something that either probes the RF or the magnetic fields to infer its position, or it's an optical tracker. It's a camera that's actually looking at the subject's face, or a marker attached to to their face to infer motion. So this is what's called the endoscout system. There's these little, this says field probes. This should, yeah, it's a magnetic probe. This is the sensor here. They're really small. And what you do is you need to alter the sequence like you would for a navigator, but it's an even shorter block insertion. So this is a basic EPI sequence. What we're doing here is we're inserting these sawtooth gradient waveforms. And then what that's going to do is going to induce a voltage into these coils based on the position of the coil in the magnet. And since we know the shape of the waveform we've inserted, we can take the voltage that we observe across the sensor and back out where in the bore that sensor had to have been to give us that voltage. It's great because unlike optical-based trackers, there's no line of sight required. You don't have to worry about openings in your head coil for cameras and that sort of thing. And you can use multiple sensors. This can work with upwards of, I think, last time I checked, 8 sensors at once. So, you can affix a lot of sensors. You can use that for redundancy or for quality assurance. One thing I like to do when working with systems like this is use multiple sensors and then track the relative position of the sensors. Sensor attachment is a big issue with techniques like this. Like, how do you attach the sensor? But you can at least QA that going forward by making sure all the sensors move rigidly. And if they don't, well, then you have an issue with sensor attachment. And one of the downsides to this technique, and a lot of techniques, broadly speaking, like this, is that they need to be calibrated. I would say that's true of all external trackers. They have to be installed and then calibrated. But most of them have to be calibrated by a service rep for that company, and that's logistically can get frustrating. Here's another example of a tracker similar to the endoscout, developed by a colleague of ours, Adam van Niekerk, which I think exploits a really cool property that I haven't seen exploited anywhere else. He manages to detect the orientation of the sensor completely passively. Whereas before we had to insert a gradient waveform to kind of wake up the sensor and activate it. Here, that's still needed. Oh, and I should just say, broadly speaking, a lot of these sensors can be activated. Here, it's activated by a gradient excitation. It could also be activated by an RF excitation. Sometimes there's a tiny sphere of fluid that's off resonance to water. So you with a specific RF activation and a very quick case-based navigator, you can find it where that sensor is. That's the difference between RF and magnetic sensors. But what I think is really cool about this is without any sort of RF or gradients being inserted into the sequence, orientation can be passively detected with the use of a magnetometer and a gravitometer. So the gravitometer or the accelerometer will find the gravity vector, right? So that will point downward along the y-axis of the scanner bore. And the magnetic field of the scanner has a directional vector, down the z-axis of the bore, or down the axis that the table slides in and out of. So that will give you two, which should be, if the magnet's installed correctly, the direction vector of the magnetometer should be orthogonal to the gravity vector. And then you can take the cross product of those to get your third vector. So I think that's a really novel way to detect orientation inside an MR machine. But to find location, you're back to the same problem. You need some sort of excitation. I think he played around with both gradient and RF excitations. I think this one might be an RF excitation. Yeah, RF detector. So there's still some RF waveform that's played, and then a quick K-space trajectory to infer that location. This is a wireless sensor, as opposed to Endoscout, which has a little wire coming off it. That's also just a practical logistic issue. When attaching sensors to patients, wireless makes things a lot easier. Kineticor is one of the big companies that's doing. So now we're on to optical trackers, and these work by putting either cameras in the bore, or cameras in a set of mirrors, cameras outside the bore with a set of mirrors, and the idea is, you're gonna optically infer patient motion. So the Kineticor works with multiple cameras are inserted into the bore. It's not a stereo-based system, to my understanding. I've never worked with Kineticor, but my understanding is these aren't used to do some sort of stereo inference, but it's used so that no matter what head coil you use, there should always be a line of sight from at least one of the cameras to this marker that is placed on the subject. The marker is what's known as this moire pattern, which is essentially a hologram, and the orientation of it can be inferred by these these holographic interference patterns that are made. So the location is inferred by the centroid here, and orientation is inferred by some sort of computation over this inference pattern, which is a cool trick. TracOline is a system we've worked quite a bit with. They're close collaborators of ours. The novelty of this system is that it's markerless. So there's no marker that needs to be attached to the subject. So what you have is this unit here that sits at the back of the bore. And then there's this long camera arm with fiber optic cable that gets spooled up, that gets attached to the table here. So this cable then runs all the way back to the back of the bore to this unit here. And here, infrared light infrared structured light is shone onto the subject's face. They can't see it, but that allows for these high resolution point clouds that you see here to be generated. And then once you have one of those, you can use those to register to the reference point cloud, much like you would register to the reference image, and infer motion that way. Care needs to be taken when using this system, because here you can see like the subject's eyes as well as the subject's nose. So you really, when you're performing your registration, you want to mask out parts of the point cloud that won't move rigidly with the skull. So generally what we do is we set up the system, get the patient in, we get a point cloud like this. We manually go on the point cloud and we crop out the eyes because we don't want blinking to interfere with the registration. and then we register the remaining point cloud. One thing that I don't think gets doesn't get enough attention. So this system sells itself on its markerless, and that is like a big holy grail for the field. But what I don't think gets enough attention is this system is calibrated by a local technician. Either every day or sometimes every subject, this camera arm is attached, right? Every time the camera arm's attached, it needs to be calibrated. But we have the ability to do that, which I think is a game changer. Calibration is done by taking a structural image of the front of the face, and then it gets sent to the TracOline computer, where that gets registered with the point cloud, and then the cross calibration matrix is derived. But what I like about this system is it puts your local center and your local techs back in control, and it's not about waiting for the service rep to show up and fixing the problem. I think that's a real game changer.
How long does calibration take?
It used to take a while. Now it's pretty quick, but it involves some other mechanisms. So we have some mechanisms so we can automatically send the acquired volume to the TracOline computer. And in that case, it'll take 5-10 seconds. When we first started working on this system, it could take a lot longer because we would have to run the sequence, manually get a USB key or something like that, and move the DICOMs from one computer to another. So it was a tedious process, but that's gotten a lot better. And I think that's something that can continue to get better because you can do it all in software. So.
And it's a per subject calibration, correct?
It's not per subject, it's per camera mount. So
per camera mount, okay.
Yeah, so in theory, if you could mount the camera in the morning and then no one ever hit it or knocked it, you wouldn't have to recalibrate. In practice, it can be a little difficult getting the top of the head coil on and off and getting the patient in and out without removing the camera. So we tend to do it per subject, but technically speaking, it's every time you mount the camera, yeah, or change the position of the camera.
Okay, thanks.
Can I ask another question?
Sure.
So generally, I think one of the tricky points with the prospective motion correction is that you need to be confident that the motion you're trying to correct for, the measure of motion you've got, is an accurate reflection of motion, right? Otherwise, you'll end up damaging the data more than the actual motion itself.
Yeah.
And in my experience, I mean, that is really tricky. That's why some systems still fall back on the good old bytebands. So what's your experience? Do you have anything like this here? Because I mean, you're detecting motion from an optical camera that's looking at the face. And in my experience, there's always a lot of twitching and frowning and sort of scratching their nose and all that things. And these are really problematic because it's very difficult to detect consistently. And I think, I would want to have a very conservative attitude on the basis that if you're not confident about what you're picking up, you might actually end up doing more damage than anything.
Yeah, that's absolutely right. You definitely need to be sure that that your motion estimates are accurate. We like, as a very basic rule of thumb, we like the estimate to be, the accuracy of the estimate to be less than half of a voxel size. So for imaging at 1 millimeter voxel size, we really want our estimates to be less than 0.5, maybe 0.1, 0.2 millimeters, that sort of thing. And yeah, you can absolutely do damage by having even just a noisy, right? Even just noise in the system can definitely do a lot of damage. Practically with this system, we found that, and again, I guess we're mostly scanning research subjects, although there are systems like this that I think are used in a more clinical research setting. We found if we really mask out, you can get really aggressive with the masking. And as long as you have, like, we find as long as you have like this cheekbone here and then the ridge of the nose, that those are pretty stable. But it's a good point. If someone scratches their nose, that's gonna.
But because people get up to all sorts of things, even in the machine, you wouldn't believe it, you wouldn't think it, right? But they do. And that's what I think, and that's, I think, one of the limitations to unfold these sort of techniques to the wider public. Because often you find, they work well on reasonably well-behaved research cohort, but then, use them on kids or, dementia patients, and it all goes out the window.
Yeah, that's a really good point. Clinical imaging is a whole other world. And I guess I didn't fully appreciate that until I went to shadow some techs who were doing clinical acquisitions, and just the range of things that they have to, have on their radar, and just the chaos that's unfolding around them was completely, in my experience, was completely different from a research setting. But yeah, it's a really good point.
And what do you do in that case? Do you sort of suspend the acquisition, or do you wait until they sort of remain still again, or what do you do?
There's a couple things you could do. You could filter. You could do some filtering on your motion estimates, right? So if you saw a large spike, you could kind of either or smooth it out, or ignore it, or just wait till it calms down. You could also stop the scan early, right? Like if you're going to get bad data, like if there is a large motion, it's probably going to affect the quality of the data anyway. So you stop the scan early, talk to the patient, hopefully get them to calm down. But yeah, I guess one nice thing about this system is it lets you know exactly what the patient's doing in there, right? It's almost like having, like, a lot of the protocols will call for, like, ABCD and so that sort of thing will call for a camera, so you can look at the patient's face. This kind of gets you that for free. I did a bit of work with Kalman filtering, right, where you use like sort of previous data and previous motion estimates, and you can compute a velocity and acceleration, and then you can kind of constrain that to what you know to be normal, what was anatomically possible, to help you filter out these things. I think Promo in theory can do that too. I started down that road. I didn't get too far, but I think it's a promising direction to go.
Because what we've done before is we suspend data acquisition. It depends on the frequency at which you have the motion information, but we can have the system sort of automatically suspend acquisition. If you think if the motion estimate you think might not be reliable, or if there's just too much motion for the correction to put up with, you can also put the acquisition on hold.
Yeah, one thing I forgot to mention, one option that's available to, I think, all of these techniques is reacquisition. So you can go by TR, and you can kind of assign a quality score to that TR. You can look at the motion or the patient's position before the acquisition and then after the acquisition, and kind of score it, right? If they didn't move at all, then that's going to be good data. And then if you get acquisitions of low quality, you can put that in some sort of priority queue. So when your scan is done, you can go back and reacquire those damaged parts at K-space. That's a really common technique that VNavs use a lot. These trackers do as well. That's probably the best bet, actually. That will extend the duration of your scan, but for patients with a lot of motion, it's probably worth it, right? Like if you have if you're doing like a 6-minute structural, you can dial in 12 minutes worth of like reacquisition time, right? So in theory, you could get every TR twice if the motion was that bad, and that is probably better than getting 2 6-minute structurals that both might be motion damaged.
And I think also if you have a good predictor of how bad the degradation is going to be, you can sort of prioritize certain sort of blocks of data over others if you're limited in time.
Yeah, I think that's a really interesting avenue of research. I don't know how much that's been explored, but you could think of a model that at any given point in time would tell you what's the most valuable line of K-space to acquire, and then you go get that one, and then based on where you might want to start at the center of K-space and then work your way out, and then based on SNR and movement, you could come up with some sort of like so no matter when you stop your scan, you would always get something, right? Some sort of image you could reconstruct out of that. Yeah, I think techniques like that are really, really interesting.
Yes, I think from what I know, often the critical point is K-space location for the movement, just based on that. But it also depends on the kind of images you're acquiring, because I mean, for sort of the MPRH style of sequences, you have a strong inversion, lots of dead time, and then long recovery. So it's quite a tricky business. But I think if you can combine how much motion took place and the K-space location, I find you can find good predictors of the overall degradation of data.
Mm-hmm.
Then you can sort of sort them.
Right.
Well, yeah.
Right.
Also, I think when you combine that with compressive sensing, to we can probably reduce the time it will take to acquire an image that's least affected by motion in a way. Some locations in K-space get oversampled, whereas others are not, right? So maybe some good combination of motion prediction and then sampling appropriately I'm guessing people have probably looked into this. This is such a straightforward thing, because compressive sensing has been around for some time.
Mm-hmm. Mm-hmm. But that's a good point too, right? A lot of the sort of like motion robust sequences out there are just really fast, right? So that you hope you get it done before the person moves, and that's always a fallback.
Deep, like compressed sensing, do you mean GRAPPA and sense, like just acceleration, or something else?
So it's more of an information theoretical technique where you only need to acquire, like, I don't know. I think I don't know if you remember Evgeny Lebed, Paul, one of our
right.
Yeah. So basically, the idea is you acquire only 50% or 70% or 30% of the K-space data, and then interpolate the rest. And because of the structure that is encoded in the data and information, you can actually recover many of them with like almost even, depending on the amount of quality you need. If I remember, I think you can one could recover like the full structural MRI, anatomical MRI from even 30% of K-space data. Clinicians did not like it at all. They won't trust it, but you can still get pretty good amount of data. So basically, the point, what this makes me think is that characterize the typical motion patterns in patients by demographics or pathology or whatnot, and have some prior for where we expect motion to be, and we'll sample that space to avoid motion. And based on these trackers, filter out that sampling when the motion occurred, or use non-motion corrupted data in that case. I think that's one way probably to improve the signal while not extending the session too long, if that makes sense. I'm not an expert.
Yeah. So there's a lot of retrospective techniques that you can do, and I'm familiar with the ones that are based off like Sense and GRAPPA or eSpirit, which really relies on the redundancy of information that you're getting on your multi-channel coils, right? And those can be used. Those are used all the time to kind of interpolate k-space where you might have missing data. If you're doing interpolation based on, so I don't know too much about compressed sensing, but if the interpolation is based on something about the properties of k-space and not the properties of like the redundancy in your head coil, I guess I would be a little more skeptical of those sorts of things, you know. And that's the motivation. That's the motivation for prospective motion correction, is because like there are a lot of tricks you can do to back out what k-space might have looked like there, but it'll never be as good as the acquisition.
I mean, that's part of the issue, is that, you know, GRAPPA and Sense, especially since it's done in image space, it's especially motion sensitive. And so if you're using an approach where you can dump acquisitions and get rid of them, that's fine. But if you're doing bold EPI, actually that's, you know, I think one of the motivation for a lot of these approaches you've been talking about, Paul, is that, and now people are using multiband, so they're not necessarily using Sense and GRAPPA as much, like using partial Fourier, but they're really bad with motion correction compared to plain old vanilla EPI, which no one really uses anymore because everyone wants the nice higher resolution that we can get with the acceleration techniques. But along for the ride with Sense and GRAPPA comes this intense motion sensitivity, which Ben Inglis, for example, is well documented on practical fMRI. So that's always one of my concerns about, you know, faster is good if you can get it fast without motion, but faster is actually bad if they're moving.
Absolutely. Especially if they move during the like all these, like, you know, multiband and GRAPPA, they have a reference acquisition, right?
Reference
and if they
acquisition
move
is critical.
Everything all entire,
and that's actually that. I would say that's, and not to go on a little side thing, but in terms of just plain EPI, and this is something that maybe you guys at Martinos have the capability of do, but like that reference scan, at least in Siemens, is so critical that not acquiring a couple of those and picking the best one, or the one where the participant didn't move, actually seems to me be one of the most kind of easiest ways to improve motion sensitivity in your scan, is by, you know, not relying on that one reference scan at the beginning of the run. And if they happen to swallow or move their eyes or wiggle that last wiggle, then you're in trouble if you're not watching your real-time reconstruction. So it's funny you brought that up, because on another project I'm working on, I want to do exactly that. Like we have access to the Siemens development environment, right? And what I want to do is so simple. Like there's that one of the prep scans is like adjust coil sensitivity, I think it's called. I think that's what it uses. Right. So I want to learn about how those prep scans work, because I want a little tweak that will just loop, that will just keep doing that coil sensitivity scan until it's confident it got a good one, right? I think that's a great idea. Yeah, I would test that for you at the end of time. Please.
Okay, great.
Because
that would go you're right. That would go such a long way just to make those techniques more robust. Absolutely.
But I guess let's go ahead. I think let's finish.
Yeah, are we on this discussion's great, so I have more slides, but if we're on a bit of a time limit, I've got all the time in the world.
I personally don't have any limit, you know.
Great. Okay.
So
I guess word for it. The last time he kept me going for 2 hours. Practically can be brutal.
Well, I mean, the longest we had was like 2 hours and 45 minutes for the Phantom QA and whatnot, you know. But we had 2 talks.
Okay.
From gold standard Phantoms and Phantom Lab. So quickly on this one, so that actually I lost my train of thought. For the reference scan, because it's a software thing, I think we can modify our algorithms to actually use the most recent reference scan in a way, right? Start with 1 at the beginning, but like after, I don't know, maybe 10 seconds or 20 seconds, can update the reference scan based on all the knowledge we have of the movement of the subject in a way, right? To basically alter the mean in a way, you know, so we reduce the error, so to say. But yeah, just a comment, you know. Yeah.
I don't know if, I mean, it's not immediately obvious to me if that's possible. It could be, but you know,
Yeah, it should be possible. It's all algorithmic, right? Just updating the reference as you update the motion parameters.
Well, so when we talk about the reference, what we're talking about is, you know, we're getting an acquisition. It's generally like right at the very center of K-space where SNR is largest, and you use the properties of that acquisition, or the redundancy in that acquisition, to make inferences about the rest of K-space that you're going to acquire and that you're going to like fill in with. Yeah, right. So just a point. When we say reference, when we're talking about like grappa and stuff, we're not talking about like, the reference volume in bold, like the first volume that's acquired.
Okay. I see.
Yeah.
Right.
Yeah.
That makes sense. Okay. Thank you.
Yeah, I mean, an issue there would be if you doing bold with an experimental design, you know, you'd have to integrate then that reference. I actually mean I think it's a good idea, is to have that continuously acquired through the scan session, but then you'd have to basically have a break in your experimental design, right? Where you would reacquire that reference and then continue on. And I guess I'm not sure, you have to be really careful about any other noise that could get introduced by changing that bit. And I'm not a physicist, so I don't know what would happen there.
I mean, I guess one could dismiss the need for it, saying people don't move as much, you know? If it's especially a highly, what do you call, mobile subject, then we'll have to come up with other things. So, but maybe there isn't a need actually. So it's probably a moot point. Yeah.
Definitely like one low hanging thing. And this is getting out of the prospective world and more into the e-spirit world. But one low hanging thing you could do is, for this coil sensitivity, like one of the prep scans, you know, you've got your frequency adjust and then your shim and then your coil sensitivity adjust. Just run that before every sequence. It takes a couple seconds. It doesn't take long. So I think the benefits to just like doing that every time. So you're not relying on a reference, you know, a reference that was taken 30 minutes ago or something like that. I think would be a big improvement too.
Definitely.
Okay, let me just, any more questions or discussions? All right, let me keep going, but just jump in whenever. Okay, so just a quick review of external trackers. They're either based on some sort of field probe, either the RF field or the magnetic field, or it's an optical based system. Most of them are marker based, but this TracOline system is markerless. If you're using a marker based system, the marker attachment issue, it seems like so simple, but you can't spend too much time considering how you do that, because of any sort of non-rigid movement with respect to the skull is going to throw off your results. So, you know, the kinetic core put the thing right on the nose bridge. That seems to work well. If you have the, pardon?
I have it works better if you put it on your teeth, right? That's the best.
Yes, exactly. If you have the budget for it and you can make a dental mode for the upper teeth, that's even better.
Yeah.
Okay, so those are some of the ways we track motion in the magnet. I'll quickly talk about some metrics we use to evaluate this, and this is by far not even close to an exhaustive list. These are metrics that kind of I've used in the past, and you know, obviously you should back out your metrics based on your study and the things you care about in your study. So one is RMS displacement, right? The root mean square displacement. This is a way to kind of compare the severity of types of motion. And essentially, essentially what it is like motions are 6 parameters. You've got 3 translations and 3 rotations. And let's say you have 2 subjects, and one is either breathing heavily or moving their feet, so they're translating in Z, and the other one is rotating their head, right? Like, how do you compare which is worse? And I think RMS displacement is a really nice disciplined way to answer that question. What it's essentially calculating is the average displacement of each voxel inside the head. And it's essentially a way to weight the severity of translations versus rotations. But what I think is really nice about this metric, and I haven't actually seen it in a publication or anything, is that's going to give you the mean displacement for the entire head, but maybe you're doing a study on hippocampus, right? And all you care about is hippocampus. So you could reformulate this metric to calculate the severity of any sort of translation rotation on the actual ROI you care about. So I think it's a nice way to quantify it. TSNR. So this is going back to the bold thing and making things worse. Temporal signal to noise, is a great way to characterize your bold data. What you're doing is you're taking each voxel independently, and you're just computing the mean intensity of that voxel through time, divided by the standard deviation of voxel intensity over time. But what's really nice about TSNR, and there's a couple papers here, is it can really help you inform your fMRI study design, right? It's really related to the GLM and what kind of signals you would be able to find, right? So here's a sort of relationship we derived with some collaborators for real-time fMRI. Showing the question in real-time fMRI is, okay, so we've got some paradigm. How long should our blocks be? Like how many TRs should we average over before feeding back some sort of signal to the subject? And there's a really nice relationship between the alpha level, like the confidence you have in detecting a signal, the signal to noise ratio, and how many TRs you're going to average over. So that really helps you inform, fMRI study designs. This is the first time I did this, I was absolutely humbled by how hard fMRI actually is. I suggest everybody just go and do it with some of their data. TSNR is brutal in bold, right? The slightest motions will kill all your SNR, right? The big takeaway for me is, yeah, maybe in structural scans and that sort of thing, there's all these sorts of prospective and retrospective tricks you can do to mitigate motion. That gets a lot harder. That gets a lot harder in EPI. So here's an example of this. When someone's not moving, a perfectly still subject with no motion correction, you get this beautiful TSNR. And then as soon as they move, you're blowing away like over 3/4 of it. PACE will buy it back to an extent. So PACE is a volume by volume, registration. And here's some work I did with an external tracker where we were doing slice by slice updates. And, we could do better than PACE, but not by much. And the question is it even really worth it at that point, right? Like if you're getting data like that instead of data like that, what's that going to do to your experiment, right? So it's a very humbling exercise. There's a lot of reasons for it. The two main reasons I would say for why it's so brutal in EPI is there's steady state effects, right? So you're exciting. The assumption is like the patient's perfectly still, and you're going to be exciting this part of their brain every X milliseconds or something like that. and that will get the T2 star into a steady state. But as soon as the patient moves, now you've perturbed all the steady states in the head, and it's going to take quite a bit of time to get that back. So here's just an example of an fMRI acquisition with quite a bit of motion. So I mean, it's a decent amount of motion, but it's not crazy, right? Like all within a centimeter here. Like these are the scale is millimeters here, so there's like no translation over a centimeter. But still, that kills your SNR when compared to something like this. But just to illustrate the effects of steady state, if you were to omit the TRs where there was motion from your calculation, your TSNR will go up a bit. But then if you keep omitting additional scans after that motion, you can buy back a lot of your TSNR. Just it kind of shows you the effect of, you know, steady state on TSNR. The other issue is these B0 effects. EPI is a really long readout with a lot of like hard turns. So any sort of inhomogeneity in the magnetic field will induce a slight deviation to your EPI trajectory. And you end up getting what we call here. So if I move back and forth and you look at this pineapple here, you know, it's the pineapple's perfectly registered, but the shape of the pineapple looks considerably different. We call that the Space Invaders effect. And there's something from Space Invaders if you guys are too young to remember that game. And to be fair, this effect is bigger in a pineapple than it is in a human head because the head is larger, but it's still a big issue in bold.
That's a fantastic illustration, Paul. Again, I'm going to ask you later for those slides. How did you move the pineapple? Did you just like poke it with a stick or something, or?
We have a pineapple. It's called a pineapple wobbler. I wish I had a slide showing that, but it's essentially it's this rig that we can strap a pineapple to with a long pole that comes out of the bore, and we can turn the pole the pole, and then we have two of them. One will rotate the pineapple, and the other one will translate the pineapple. So.
That's actually that's awesome, and I think this brings up one of the things that at least Pradeep in this group in general has always kind of wanted to do, which is replicability as we're testing techniques, right? Like one of the issues if we're looking at how do we deal with motion that I've always found is like you can tell someone to go on the magnet and wiggle around to, you know, and I've done that to test VNav scans T1 and T2, but getting any kind of replicability across testing different approaches is really difficult. So I actually love that idea of having a way to manipulate a phantom, or, you know, pineapple's actually great. The pineapple's usually better than phantoms for EPI scanning, to be able to test different approaches. So that's might email you offline about that later.
Sure. Yeah, absolutely.
I think the thing we should be thinking about is how through these techniques we can evaluate them with consistency in some way and not have that be dependent on whatever random squirmy subject we have in the magnet at that moment in time.
Absolutely. And our pineapple wobbler, it's a lot better than not having it for sure, but it's not perfect. And, you know, I've spent some time thinking about how you could build a rig and actually, you know the sort of displacements down to the sub-millimeter, right? I'm not a mechanical engineer, but surely you could build something out of like, you know, PVC plastic or something where you can insert things in multiple ways and then measure the displacement outside of the bore with some sort of laser or something like that. I mean, I've thought about this. I haven't actually, you know.
Yeah, I think that's important in figuring these techniques out, though, probably, right?
Absolutely.
Especially testing the optical ones too, because you could stick a marker on that or have your camera on that and then know the real true physical displacement we are moving, and then see how that's reflected in what's being recorded by your prospective system. So yeah.
One thing the EndoScout guys have is they have this giant cube that fits into where you would put a head coil, and then the cube has a bunch of little square openings in it, like maybe 10 by 10, right? And then they have this long sensor stick that has maybe 10 sensors on it, and they put it into each hole, get measurements, put it into the next hole, get measurements, and that's how they do their calibrations. So they know that when the sensor stick is put into this cube, you know, it's exactly 10 millimeters or whatever it is away from the adjacent one, and that sort of thing.
Okay, that makes a lot of sense. Yeah.
Yeah.
Can I ask just a small question about this steady state effect? Here, the results you show, it's you compute the TSNR after correcting for motion, right?
Yes. Yeah. This is after. Yes, this is. I believe it's been a while, but I think this is after a slice by slice correction for motion. And we're just admitting.
Okay. Because I wonder if it's, how can you be sure if it's the steady state effect or if it just remaining motion near the transition phase, if you see what I mean.
It's a good point. Yeah, if there is motion, it's not the bulk motion. But yeah, that's a really good point. I guess. So what could we do? I guess we could start omitting random sort of TRs where we don't think there's motion.
Okay.
And then that shouldn't change the TSNR. I guess that would be an interesting analysis.
Okay.
But yeah, that's a really good point, because especially here you can see there is some motion, right? There is some relaxation.
Yeah. Okay. And on the previous slide, you was showing the pace. The last one is a prospective motion correction techniques.
It's prospective, yes. Yeah.
I'm surprised it does not improve the SNR that much. I would expect prospective really solves the problem. So why is it so? If you have a perfect prospective motion, you see what I mean? You should have the same thing as if there was no motion, right?
Well, this is a question I was going to ask you, Paul. Oh, sorry, Pradeep.
It's okay. So I was going to quickly mention that, see, there's a big debate in the group about how we define SNR. Okay, what is signal? What is noise? You know. So a quick promo to an upcoming talk next week on October 12th, where Professor Thomas Liu is going to give an overview of, you know, all sorts of contributions that are happening to noise during these acquisitions. You know, here we're just talking about motion, but there is other confounding factors in terms of breathing and whatnot that are actually also causing changes in signal and noise, right? So I highly recommend you join us next week, right? And not take these SNR at like a bit more too literally. I think changes are helpful, but there is more going on than that can be easily observed and tested, if that makes sense.
Yeah, and yeah, like so why is the TSNR hit in EPI so brutal? I do think it's a combination of steady state and V0, but I wouldn't have believed this until I computed it myself too, and this is why I think it's such a humbling thing to do. It really drives home. Yeah, how.
I mean, I guess like a question for you, Paul, is that like with Prospective, we still can't undo what's happened, right? So if the participant moves during a bold EPI frame, then what's getting excited and read out is not what we intended to be exciting and reading out based on what the scanner thinks it is. And there's no way to undo that, right? The only thing we can do is use that information to then try to apply a correction to our next data point. So is that really kind of what's driving this hit, is because there's no undoing what's in the past, and that's still going to impact our calculation?
In bold, it's hard. You're right, because if you have any sort of paradigm, you can't just reacquire that, right? What some people do, if you're not doing a paradigm and you're just doing resting state, what some people do is they'll just go until they have X minutes of good resting state data, because that's not really, you in a sense, you could go back for resting state, right?
Right.
Yeah, but with the paradigm, yeah, once it's happened, it's happened, and you can't go back. But I really think the TSNR hit is due to steady state and B0.
I think that makes sense. Yeah.
And just one more metric, because I work in the free surfer lab. One thing we're always concerned about is how do things change the cortical volume and thickness estimates. And just here are a couple of papers from some colleagues here. The first one showing if you take, this is done with VNAVs, if you take all the data acquired, there's some pretty strong trends of more, and this is in RMS displacement, which I mentioned earlier. There's some pretty strong trends of, like, the more displacement, the more bias you're inducing into your estimate. And then the scary thing about this paper is, even after it was QA'd by a radiologist, I believe, I don't know for sure, but I think it was QA'd, and all the images that weren't considered diagnostic quality were discarded, you still see the effect, which is kind of troubling. More recently, a colleague, Rob Frost, showed that with using an external tracker, where you can actually update your field of view within an MP-RAGE echo train. So in MP-RAGE, you might have like one excitation pulse, and then you might have a bunch of smaller inversion pulses, and then a large excitation pulse again. VNAVs will only be inserted, after the excitation pulse. So with VNAVs, you don't have the ability to update your field of view within the echo train. So he's shown more recently that this will improve on the this sort of thing. Okay, yeah, I think that's it. Thanks, guys, for listening, and thanks for the interesting discussion. And I just want to thank all of my colleagues and collaborators. They're not even all listed here, but I'm just one part of a big team. So none of this would have been possible without such wonderful collaborators.
Can you quickly go back, Paulo? Maybe we should do a big clap to the fantastic talks so far. Yeah, thanks. So in the last slide, so on the left plot, you said, even though radiologists could not detect any motion, that's what you mean by diagnostic quality, right?
Yeah, so my understanding of the method, and I could have this wrong, but all the images were scored by a radiologist, and they were told to discard anyone that wasn't considered diagnostic quality, and that's the second figure here. Yeah.
So I would take that to mean that there was no visible motion in the image.
Correct.
Or at least, I mean, yeah, at least not in the areas they probably looked, I guess, so they may have not looked everywhere, but we have the independent motion estimation data, and then you plot it here, and you can see that more motion leads to decrease in both volumes and thickness. Is that decrease expected, I guess? After all, these are all, again, estimates, right? Thickness and volume, both are estimates from the image.
Yeah, is it expected? Let's see. I mean, I guess I would have to think about
right, yeah. So I mean, if this was, let's say, estimates from a phantom, which allows estimation of volumes and thickness, for example, then we can definitely
check.
Yeah, I was just curious. Yeah.
It's not obvious to me. I have seen this result, and it's a very important one, but it's not obvious because if you think of motion, it will mostly blur the anatomical image, and I would expect actually the opposite, with a blurred gray matter having a segmentation that will lead to more volume. But so I was surprised to this.
It depends on the demographics side. Do you remember the demographics for this study?
No, I don't think so.
Well, we know old people move less, right? At least in task fMRI, if not everywhere.
Yeah. Now, for me, the important message of it is that having a binary QC, as we all do, is not enough, because there is a continuous motion effect, and there is a continuous relationship of the motion severity to the end cortical thickness. So having a binary decision is quite useless in this example. This is what it shows, no?
Yeah, good point. That's what Doug Grieve told me when I gave a talk in the FISA for that. We'll have to make much more localized decisions about quality.
Quantify one,
yeah.
It would be nice to quantify the severity of motion.
Yeah,
maybe
cool.
with external marker.
Yeah, it's been fascinating. Any other questions for Paul, Dr. Paul Wighton, before?
Maybe a last question would be, so we've been using Firm, which you're probably familiar with, Paul, from Damien Farah's group. I guess, would you have any thoughts on kind of just the tracking? Because I was just kind of looking on the side at the tracking information from something Track Innovations is kind of selling their product right now as a tracking system, not necessarily an active system unless it's for research. So in my mind, that the only thing you can do there mostly is talk to the participant after that run, if you're doing bold, and try to see if you can get improvement. Or do you have ideas of other ways that kind of real-time-ish data could be used beyond subject participant encouragement?
With Firm, you mean? With the Firm system? With
Firm, or even if you were using the TracOviz product in that kind of way as a motion tracker, not as a motion corrector.
Right. So you're just you're just tracking the motion of the subject. Yeah. So my understanding is, like, Firm's goal is they want to inform the tech that the scan isn't going to be good quality before it finishes, to get them to stop and try something else. Other things you can do, but other than check in with the subject, I don't have any good answers. So one thing I've seen,
that's the response that I have too. So I was just wondering if you. So yeah, okay.
One thing I have seen, which I guess I'm a little skeptical of, is some sort of like feedback to the person in the scanner, and usually it's done for kids, like to like, okay, like you're controlling the little video game character and you want to collect all the coins, and you do that by staying in the same spot or something like that.
Yeah, and
I'd be worried about the kid be like playing with the game and like making the motion even worse with that's some sort of paradigm like that. But yeah, other than checking in with your subject, I don't have any good answers.
Okay. Nope, that was kind of my response too. Thanks.
Before we close, do you want to take a few minutes to talk about open challenges, Paul? I guess you probably touched upon them in each subsection as you went through, but just like any parting thoughts, research opportunities and whatnot.
Yeah, I mean, I think the calibration process is the least explored. Like when people compare and evaluate all these trackers, I think not enough attention is paid to calibration. And other open challenges, there's a lot of different trackers now, and like John mentioned, none of them are really for clinical use. So I guess that's the challenge now, is how do we get these into not just research use but clinical use? And then the issue is like, well, we don't want to make the data any worse. And then there's all sorts of problems with either noise from the tracker or some sort of unexpected behavior might end up making your data worse. I think those are all like really, big challenges now.
Yeah, the last point is fascinating, that how can we avoid making it worse, That sounds like a nice project using phantoms to try to validate the methods, right?
The problem with phantoms is their behavior is very, very expected, right? If you did it in a phantom, I wouldn't be convinced it would work in subjects who I can't remember who, I think it was Antoine who mentioned this, like who might scratch their nose or hit the camera or that sorts of thing.
Right, but at least you have a gold standard, right? So, for example, actually, we were talking about another paper in the group on dynamic phantoms from New York University. Sunny, forget exactly. They'll give a talk soon. They designed these dynamic phantoms with controlled movement in order to actually closely estimate SNR that resembles actual resting state fMRI data, right? Because their interest was to improve SNR with more accurate baseline, right? This actually goes back, there's probably some links to how we can improve motion correction based on dynamic phantoms too, right? So for here, what we notice like what you call opportunity to validate our motion correction methods because we have a known amount of motion, right?
Yeah, so I think that would be really valuable. Yeah, for sure.
Going back to your earlier discussion in the talk, where is rigid motion all we need? That's the question. We know it's not rigid, because what we are estimating is what we can see on the surface of the head, but we know the brain moves in a nonlinear fashion inside the CSF. If at all, if it's moving sometimes, we don't know. It's all just on the surface, right? So that way we can correct for any edge cases or mistakes at the boundaries made by these methods using phantom data. I think that's one interesting opportunity.
Yeah, that's a good point. Any sort of rig that will let you confidently know what the displacement is to the sub-millimeter level would be super useful. I can't comment. I don't really do any work with non-rigid stuff, but I that is a problem, especially at higher field strengths. But yeah, I wouldn't even know where to start with that.
Following up on this, since you've worked with these systems, Paul, one of the kind of continuous concerns, and this is not the non-rigidness inside the brain, but just the skin versus the skull in the brain, right? The trackers, and why it's I've heard that kinetic core, it's better to attach it to the teeth even versus the bridge of the nose, because your skin moves, and especially when your participant's padded in the coil, you have pads which are kind of pulling their skin, which means that even more than typical, like when we're typically here in air, probably our skin motion is very tied to our skull and brain motion. But when you have padding in, then you're pulling your skin. And I guess, what are your thoughts on how big of a challenge that is? It sounds like you've gotten pretty good results, or is this still something that's really going to have to be overcome for getting violence in?
Yeah, so I mean, yeah, the sensor attachment issue is a really big issue for sure. I've gotten good results with compliant research subjects, right? Will that translate into the clinic? Probably not, right? Yeah, so that's a big issue. I wish I had worked on a study where they were making dental molds, or I've heard of either other ones, like if they're doing surgical implants anyway, they're able to like affix something directly to the skull based on some sort of surgical implant. And yeah, I would say clinically, I wouldn't know how you would do it without at least a dental mold, right? I think that would have to be the minimum for something like that.
Sorry, because I missed the beginning of the talk, but did you talk about the optic way to track the, instead of Kineticor, there is a new one called TracOline, which has not this. Okay, sorry.
No, no worries, no worries.
Then you don't have a need to attach a marker on it. So it sounds to me it's really a big improvement compared to Kineticor, but I don't have any feedback on it.
Well, but I guess my worry is still skin. Right?
Yes, TracOline, yeah, exactly that.
You're still tracking skin. So if I hold my skin and then I move my skull, I know I can move my skull and have my skin not totally track with the skull motion. So
yeah, but it's then a question of global motion versus local motion. So I would get it's kind of more robust. I would expect it to be, no?
I've never worked with Kineticor, but I would say it's more robust than the EndoScout, which I have worked with for that reason. But essentially, you're shifting the problem, and maybe it is, to be fair, an easier problem to solve. But the problem is no longer a sensor attachment problem. It's how do I mask this point cloud so that I'm not registering, non-rigid motion, right? So, and you can actually get pretty aggressive with the cropping of this point cloud, right? Like as long as you have the cheek and the nose, the cheekbone and the nose ridge, we found that works. We found that works pretty well.
Okay.
Something that Maxim Zaitsev started doing back in the day. I don't know if he ever got anywhere with that, but he was planning to use like not one marker on the skin, but two. So maybe you could come up with something equivalent here. On the basis that, if you have two markers, then you can monitor the sort of the distance between them and their orientation and see if the detected motion is consistent. Do you see what I mean?
That's a great idea. Yeah, I mean, that's something we do with sensors, but.
So maybe you can do the same for those that don't use like optical markers. Maybe you can find landmarks, I don't know, between the, the end of the eye and the tip of the nose or wherever, and see if that remains consistent through the scan.
Actually, I think that's a great idea. But because maybe even with this system with TracOline, because you're not doing the Kineticor moire pattern thing, but what if you just put, like they do in motion tracking for movies, 2 IR bright dots? You can either paint them or a little sticker, one on the nose bridge and one on the cheekbone. That actually would be a good measure then of how much you are tracking due to skull and bone motion and how much you're tracking due to skin motion.
Right. It's like once you have multiple markers, you can start doing.
At the moment, when I remember when he was talking about it, it all sounds very good in principle, right? But the devil is in the detail. I mean, when you're trying to find objective measures of whether a certain skin motion is acceptable or not, and what scenario it works, what scenario it doesn't, and things. It's all. I mean, it's really not. Yeah, it's fiddly. Like.
I really do like the idea, though. You could think of like just making 2 ROIs, right? I'm going to have one ROI, which is like the nose ridge. I'm going to have one ROI, which is the cheekbone. And those are my 2 virtual sensors. And then I can do all my QA tricks, right? Like what's the relative distance and orientation, right?
Right. It's like you're flying and you have your pilot flying and your pilot not flying instruments, and they have to talk to each other. And when they don't agree, then you have a problem. But if they agree, you should be good to go.
Right. There's also like robust registration techniques that will try to like ignore deformable parts of a model. I don't know if those could be done in real time though. I think that's the issue there. There's like sophisticated registration techniques you could throw at it, but are they quick enough to do in real time? I'd be skeptical. Maybe.
So Pradeep, I think in terms of, to get back to your question earlier, what the sort of big steps going forward would be. What I find quite shocking sometimes is that, most often than not, people don't know how much motion took place during the acquisition of the data. So they try to, and it's not actually, it sounds like a trivial thing, but it's not at all. I mean, if you ask people, okay, how much people did your participants move more often than not, people just don't know.
Right. Are you recommending that everybody should measure motion during the acquisition?
Well, I'm just sort of expressing the wish that if there
No,
was,
no, that I'm thinking it of. I'm thinking of it as a best practice thing, like a QC protocol. You know, if you want to be sure that no motion happened, you have to measure it. You know, if you don't measure it, you would never know, right? So this brings us to a question of: is there a cheap, reliable way of estimating that motion occurred beyond certain acceptable threshold? I mean, I guess any motion is not good, but it's good to know if it's like within 5 mm or a centimeter or more, you know. So I guess we have to let's ask Dr. Wighton on this.
Yeah, I mean, I guess it depends on the sequence. You know,
Right.
structural sequences you can always reacquire, so motion is less devastating there.
No, as in, I guess the question. Sorry, sorry to interrupt, Paul. I think if I understood Antoine correctly, he was saying that most people don't know how much motion occurred in the retrospective category. Am I right, Anton, or did I?
yes, I'm not even talking about predicting the impact of motion on data quality based on the sequence and things like that. I'm just sort of low-level information of how much motion took place.
Right.
To me, you know, you would allow people to make a lot better, more informed decisions on what to do with the data. I'm not even talking about you know, how to account for predicting degradation and correcting for it. Even a ballpark estimate of how people behave in there.
Right. They basically something like the firm approach. You know, you measure, you like right after the acquisition, just see if you have quality data or not. In the case of resting state data, you can estimate that. In the case of other things, you need some sort of measure using a tracker and whatnot, right? So the important point being that if you didn't measure the motion, you actually don't know, right? Because as I sit with the techs and RAs here, people are not looking at the patient to see, you know, even if they're looking at it, it's impossible to tell when small movements happen unless you like have like continuous video or whatnot, you know. So it's something to think about. It's a good question. Like, should motion measurement or tracking be required as part of a protocol, you know?
I mean, so this might be a situation where navigators are a good fit, right? Like even if you didn't want to do reacquisition, or even if you didn't want to prospectively correct, you know, you could run a navigated sequence and at least quantify motion, right? And then you can do that without any sort of external hardware or like calibration or anything like that. So that might be.
Can that be done a week after acquisition? I guess without K-space, maybe we can't, right?
You can. Well, I don't know about promo, but with VNavs, the motion estimates get written to the DICOM, and there's some code on GitHub where you can just pull them out. Yeah.
But that still requires VNavs, though, right?
Yes. Yeah.
Oh, well, that's a software solution, so it's not so bad, though.
Yes. Yeah. So if any of you guys have Siemens scanners, you can ask your Siemens rep for the VNav sequences. You should be able to get them from them.
Yeah.
I mean, that works for MP-RAY or inversion recovery style sequences, right?
Yeah, exactly. Yeah. So it's like MP-RAGE, maybe T2 space. I don't know. I don't know what the whole list that's available.
I believe I mean, as an external user, not an MG8 per site, they work really well in my experience. I went in there and wiggled, and I thought it got a really clean scan, and we've been starting to use them as our standard scans. So it's T1, T2, and so the T1 at MP-RAGE, T2 space, and also multi-echo MP-RAGE. And that's kind of what we started to settle on, is using the Navigator guided multi-echo, which I think maybe is an ABCD standard scan. I can't remember, but ABCD is definitely, that study is using the Navigator guided scans to their standard anatomical acquisition, because they're doing kids, and it makes a lot of sense, and it seems to work well.
Cool.
yeah, highly recommend it to grab them from MGH.
Okay, thanks for the advice. That's good to know.
Can I?
Fabulous. I guess, yeah, any other questions? But I think we can probably.
Do I have time for a more technical question for Paul?
Sure.
About the RMS. Actually, I work a lot about this parameter because I'm working on motion simulation. So in this case, you take a clean image and you simulate motion and look at the results, and so one of my question was to how to quantify this amount of motion. And for sure the RMS is a way to go, but I get some technical difficulty because it's really related to the center of rotation. And if you have a rotation with a center at the corner, you will get a very different amount of motion in the brain. So and when people talking about a rotation of two angles, they always refer to a rotation at the center of the volume.
That's my understanding is this, and I think it even says it in the text here. This equation here assumes a sphere, and it assumes it's centered on isocenter, I believe.
Yeah, it's on the isocenter of the sphere. Yeah. Then to apply it, you have to express your motion at the isocenter of your brain, right? I think this is a point to not forget.
Right.
So that it makes sense.
I mean, yes, yeah, it's a very good point. But especially if you're doing a simulation, you should be able to just mask the voxels you care about.
Yeah.
And then just measure directly how much they've displaced and then take the mean, right?
Yes, but then I did some plot to compare the mean compute on a mask of the brain versus this formula of your RMS, and I get a huge difference actually. But
that's
because the brain is not a sphere, so depending on the shape, you get a very different mean for the same rotation, of course.
Yeah, and oftentimes the rotation of the head is like the point of rotation is the back of the skull, right? Because you're resting against the pillow and doing this. So I mean, I would trust it. I would trust your metric more than that if you did it that way. This is more of a this is a rough approximation. It just gives some
but
weight.
everybody use it, and it's the difficult. Yeah, okay. But the difficult, my metrics takes time to compute. Maybe I don't have the good way to do it because you.
Oh, I see.
You compute a displacement field on the whole, so I probably program it badly. But okay, never mind.
Right, but it's a good point. There's a lot of assumptions in that metric. Yeah.
Yeah, it's a great point, Romain. I mean that from where I see it, it sounds like an opportunity to improve the best practices, if I can put it that way. And I think we can even borrow from the registration literature. We know there is a lot of work on computing localized correct displacements, for example, diffeomorphisms and whatnot, that are actually pretty accurate. So we can borrow some advances from that literature to improve the amount of displacement that occurred at each voxel.
Which literature? I didn't get.
Registration, like registering two images, alignment. Look into something called diffeomorphisms too. They're pretty good.
Yes, but registration is just computing an affine between two volumes, and then the problem is how to quantify this affine in terms of.
Right. Yeah, they have many metrics in the literature. Diffeomorphisms are good approach in my understanding. So we're running at like an hour and 50 minutes. So this has been fantastic. I learned a lot, and I think many people in the community would also appreciate this great service by Dr. Paul Wighton for his effort and time for kindly sharing his expertise and knowledge and helping us. Thank you so much, Paul, again. And thanks everyone else for joining and making this a great discussion. Keep coming back for all the talks. You know, the next one is very interesting and related to. We'll have one more on dynamic phantoms and etc. So thank you so much.
Thank you guys. I really appreciate the lively discussion. This was great.
Yeah, thanks so much, Paul.